All right, so aren't you glad buffers is over? So the next two chapters deal with amino acids and proteins. So if we look at your big divisions of biomolecules, you got your carbohydrates and your lipids and your nucleic acids. So, and then you got your proteins. So, and these are all, most of these anyways, not all of them, but most of them are often in the form of polymers. So what's a polymer? Yeah, it's where you attach multiple monomers in a chain. What are the monomers for proteins? Amino acids, and that's why we're starting with this chapter on amino acids. You put a bunch of amino acids in a chain, you link them together covalently, and you get a peptide. And long peptides we call proteins, and you put multiple peptides together and you get bigger proteins that have multiple subunits and all this stuff. So, but we have to start at the very basics and talk about the individual monomers. So throughout this class, we'll get to some of the other biomolecules as well. Part of the class will deal with nucleic acids, a little bit of lipids, some carbohydrate stuff. So, but for these two chapters, just amino acids and proteins. So your amino acids and proteins. Proteins are the most diverse of your biomolecules, the greatest variety in them. And we'll see that's why they're often the most, you find them everywhere in the cell. They're the most useful for a variety of reasons and stuff like that. But we'll get to that later when we start talking about proteins specifically. But we've got to start first with just talking about the monomers, amino acids. What is an amino acid? Well, it's an organic molecule that has two functional groups. What functional groups? An amine group and carboxylic acid. Sweet. So there are lots of different molecules that could be called an amino acid that have an amine somewhere and a carboxylic acid somewhere. But we're actually getting more specific than that. When we say amino acids in a biochemical context, we usually mean specifically alpha amino acids is usually the way we say it. So if we look at a carboxylic acid here, so there's a carboxylic acid. What do we mean when we talk about an alpha carbon? So it's the one adjacent to the carbonyl carbon. So it's always the one adjacent. That's alpha. The next one over would be beta, gamma, delta, so on and so forth. Play with your Greek letters. So, but he's the alpha carbon. And so when we talk about alpha amino acids, it means the amine group has to be attached to that alpha carbon. There are other types of amino acids out there. So it's just none that are normally incorporated into proteins or anything like that. So this is the only type we're going to talk about. Now on this alpha carbon, besides having an amine group, what else do we have? Yeah, we have hydrogen, and then we have some side chain that we say. And this is what makes different amino acids different from each other for the most part. So what is this R group? So when is the only time it's not a carbon chain of some sort? Glycine. What is it in glycine? Hydrogen. So glycine, this is just another hydrogen. And because it's just another hydrogen, this is not a chiral center for glycine. So, but for every other amino acid, this will end up being a chiral center. And there's an R version and an S version. Or for amino acids, we usually talk about an L version and a D version. So which version is typically the only one used by living organisms? L amino acids. So remember that, because when we get to sugars, for sugars, it's usually D sugars, but for amino acids, it is the L amino acids, which typically correspond to the S amino acids. Notice which amino acid does it not correspond to an S amino acid? Glycine, because again, glycine has no chiral center. There is no RS if this was glycine and that was just another hydrogen. But for all the rest, it's that way. So there's also one other amino acid that doesn't quite have this general structure. It has its R group as a big ring attached to the nitrogen. Which one is that? That's proline. So, and that puts some rigidity into the structure for proline and stuff like that. But again, the key is that most of them just have this generic structure. So how many amino acids are pretty typically occurring in living organisms? About 20. There's a funky oddball every once in a blue moon in some random organism and stuff like that, but there's 20 general amino acids pretty consistently across any organism you find. And it's just 20 different R groups is the difference. The acid part is still the same, the amine part is still the same, so on and so forth. Cool. So we got a carboxylic acid group here, and I drew it as you'd normally see it as a carboxylic acid, so from organic chemistry. And here we have an amine, and this is how you're used to seeing amines in organic chemistry. So, but if you put this amino acid in water, you're never going to see this. So it's never going to be a predominant structure in an aqueous solution at all. So I'm going to do this one more way. So for an amine, amines are your organic versions of what? So base. And your carboxylic acid is the organic version of an acid. So this is the basic form of the amine. His conjugate acid would look like this. So I'm going to put these both in their acid forms because it's the acid forms that have a pKa. Bases don't have pKa's. What do bases have? pKb's. So when they're giving you the pKa of the amine group, what they're really giving you is the pKa of this conjugate acid form. That's what they're giving you. Cool, so now that these are both in their acid forms, I can talk about the pKa's of both of them. So the carboxylic acid group for every single amino acid falls within a very narrow range, and we just say they're all about what? All about equal to 2. pK is all 2 for most of them. So, and for the amine group, it's a little bit broader range, but the pKa's are all kind of where to where? Yeah, somewhere within 9 to 10. There's a couple of oddballs that get out of that range a little bit, but that's for the most part, we just assume they're 9 to 10. These are numbers you need to memorize. Carboxyl group pKa, 2. Amine group, 9 to 10. Cool. Now, if they give you exact numbers, by all means use the exact numbers. But if they don't give you exact numbers, these are the numbers we expect you to remember in your head. Now, the R groups. So several of the R groups also have acidic or basic properties. Did you guys have to memorize pKa's for those? Or are those going to be given to you? Given to you. Wow, you guys are lucking out all over the place. You don't have to memorize the structure of all the R groups. You don't have to memorize their pKa's. Back in the day when I was in biochem, they made us memorize all that stuff. And I had to walk to school uphill both ways in the snow in Arizona. So, or something like that. Biochem is one of those classes. Like you guys are the 300 level. Obviously there's a 400 level majors class. They usually get a little more assigned to them. But even amongst those classes, depending on who your professor is, some professors might be like, oh, why would you memorize those? You can look them up in a book anytime you'd want to. And so what's required out of a biochem student can be a little different from professor to professor. So, but I like that you actually don't have to memorize these, especially because you guys aren't biochem majors. Are you really going to need this someday? Come on. But here's the deal. You are going to need to know these two pKa values, and you're going to need to know what to do with these lovely pKa values. Cool? All right. So one last thing, and I totally forgot to show this. I said that the chirality center here, what kind of chiral center? L. And if you look at, we can draw that in a couple of different ways. So for a Fisher projection, your most oxidized carbon always goes at the top of a properly drawn Fisher projection. What's the most oxidized carbon we have on that structure? Yeah, the carboxylic acid one. Sweet. And you run the carbon chain down the vertical. And so in this case, this is the alpha carbon. And the R groups are usually containing carbons. And so the vertical part of it, that's the carbon chain. To be an L amino acid, it means that the amine group has to be on the left side of that Fisher projection when it's properly drawn. So, and over here is just the alpha hydrogen. Cool. So you can also draw that out in one other way. All right, so wedges and dashes. So here, with Fisher projections, that's where we normally assign D and L. But normal line angle formulas, that's where we usually deal with more R and S. So let's deal with R and S. Who's my number one priority group off my chiral center? Nitrogen beats carbons. Cool, who's my number 4 priority group? Hydrogen. So, and who's number 2 and number 3? Carboxyl group's always going to be number 2, and your R group's typically number 3. That's typically the way it works. Cool. So your circle doesn't need to include number 4 at all. Just go 1 to 2 to 3. And what kind of a turn, if you were turning a steering wheel, would that be? Right-handed turn, which corresponds to R. Now here's the deal. It corresponds to R if you're facing the molecule from the correct side. So to face the molecule from the correct side they decided to assign thing is when your 4 priority group is on the dashed bond, is directly behind you. So if in this case the number 4 priority group was on the dashed bond, this would be R. And I would have put him as the dash. Don't write this because you're going to erase it in just a minute like I will. And I would have put him as the wedge, and that would be an R amino acid. But that's not what we want, right? If I want one of the actual physiological amino acids, I want the S form. Well, just switch who's the wedge and who's the dash. Sweet. Okay, then I'll make the hydrogen the wedge. I'll make the R group the dash, and boom, there's your S amino acid. So you can draw it in Fisher projection, you can draw it in line angle form. You should be comfortable drawing it in both, just FYI. Cool. So when you look at the general structure of an amino acid, look polar or nonpolar? General structure. Well, what interaction is the amino group capable of? Hydrogen bonding going on over here. What about the carboxyl group? Potentially hydrogen bonding as well if it's still got that H, but acceptors regardless. So it looks pretty polar. And so I get a lot of students be like, Chad, they were teaching me that some amino acids are polar and some are nonpolar, but they all look polar. What's going on? Well, all amino acids are polar from a general chemistry perspective, but that's not what we mean when we put them in categories. When we talk about amino acids being polar, nonpolar, acidic, basic, all we mean is actually just the R portion itself being polar or nonpolar or acidic or basic. That's what we mean. So your general classes of amino acids, you should kind of know which ones are polar and nonpolar, acidic, basic, and kind of have general classes. So even more so though, you should be able to recognize from their structure if the R group is polar, nonpolar, acidic, basic. So suffice it to say, I would memorize who's acidic and basic. Who are the acidic R groups? Glutamate, also called glutamic acid, and aspartate or aspartic acid, same diff. So those are your two acidic ones. So, and we'll see that as acids, they don't look like acids because at pH 7, they exist in their conjugate base form as carboxylates, why we might call them glutamate or aspartate. So I remember that they look very similar, but they're carboxylates, carboxylic acid groups. So, and that's why they're acids. But they exist typically predominantly in their conjugate base form, and they have a negative charge. So this will seem a little crazy, but the acid groups at pH 7 have a negative charge. They're the ones that normally get your negative charge pH 7. I remember when we had to memorize the structures, I always remember that glutamic acid was 1 carbon bigger than aspartic acid because your glutes are big, so glutamic acid was bigger. Aren't you glad you didn't have to memorize those lovely structures? So who are your basic amino acids? So lysine and arginine, definitely. Some books will include histidine, like your book, and some professors as well, and some will say, So lysine, arginine, histidine is what you need to know. So, and lysine and arginine definitely are considered basic amino acids kind of universally. Histidine kind of depends on who you talk to, but you guys should consider histidine a basic amino acid for your class. So if you look at lysine and arginine, first off, lysine and arginine, okay, they're bases because they're amines, and amines are organic bases. But at pH 7, even though amines are bases, they predominantly exist in their conjugate acid form. An amine, what's the conjugate acid form of an amine? What charge does it have? Positive charge. And so we see that for the basic amino acids, lysine and arginine, at pH 7, they predominantly have a positive charge. They're the positively charged R groups. Now, histidine's a little funky. And we'll see that histidine is kind of quasi-basic amino acid. So, but at physiological pH, histidine, at least free histidine, actually will probably predominantly exist in its base form, not in its conjugate acid form, in its neutral form. There will be some positive charge around out there, so on some of the molecules, but most of them will actually be in the neutral form, so it's a little bit funky. Now the pKa's of these R groups that we're going to see here in a little bit, those are for the free amino acids. If you actually put these in the context of a big protein and a big long amino acid chain, those pKa's all change based on what environment it is in the actual protein. And so histidines can actually get a little more basic than they are freely, and that's why they're often considered on this list. So they often act as base in different enzyme mechanisms and stuff like that. And so they usually get tacked onto this list in some books. So, but lysine, arginine, histidine, basic, aspartic acid, glutamic acid, or aspartate, glutamate are your acidic ones. So one thing to note, don't get confused between glutamic acid and glutamine, or aspartic acid, aspartate, and aspartamine. So, or asparagine, I should say. Not the same. So asparagine and glutamine, those are amides. Amides. Amides are not acidic or basic at all. They're polar, but they're not acidic or basic at all. So know your 3-letter codes. You guys got to know the 3-letter code. So back in the day, we had to memorize the 3-letter code and the 1-letter code. So in the 1-letter code allows you to get really ridiculously geeky t-shirts like this one. This is cysteine, histidine, alanine, and aspartic acid, and it spells Chad. That is the Chad peptide in the one-letter code. So for the student that bought me this, thank you. So again, you guys don't have to know the one-letter code for your class, though, but you do need to be familiar with the three-letter codes. So notice aspartic acid, ASP, whereas asparagine is ASN. So know the difference. Cool. So a little lovely table on your handout that just kind of shows you the difference between the nonpolar, the polar, the acidic, the basic. Definitely memorize your acidic basic. Just go look at the structures in your textbook between the polar and the nonpolar, and you'll see that the nonpolars, pretty much ours, are all carbons and hydrogens. They're just hydrocarbons for the most part. Whereas the polar ones are often like alcohols and have hydrogen bonding, or cysteine has an SH and is capable of hydrogen bonding and stuff like that. Okay. Then definitely memorize which ones are nonpolar, which ones are polar, and definitely which ones are acidic and basic. Cool. So last thing we're going to do with these amino acids in a little bit here is dealing with the PIs and the pKas and what form predominates and stuff. I know that's a big point of confusion, so that's why we're going to save it for last. That way, hopefully, it's the one big thing you remember from this section. The last thing we're going to do, though, is we're going to take this amino acid and start putting them together. So if I put another amino acid next to this guy, and again, I'm not actually drawing this in structures reflecting pH 7 by any stretch of the imagination right now, just FYI. We will do that shortly. So, but what you'll find, and technically at pH 7, this usually exists as a carboxylate, and so on and so forth, and we'll see that in a little bit. So the only reason I draw that, though, is what you find is that the amine group, at some way, shape, or form, is going to end up attacking the carbonyl over here to put two amino acids together. So, and ideally, you can just look at this as being a condensation reaction. So when steam condenses, what forms? Liquid water. And in this case, you can see that two of those three H's and the O are going to be gone. So it forms a small molecule liquid water. So as a result of the condensation process. So, but you put this together, cool. This lovely bond right here is part of what functional group? Functional group is this whole thing. Without the carbonyl, that would be an amine, but with the carbonyl right next door, it's not an amine anymore, it's an amide. Your peptide bond is an amide bond, and that is a fabulous thing. You guys might remember from OChem 2, but probably not, as I'm guessing, that your amides are the least reactive of the carboxylic acid derivatives. That is a fabulous thing. Because I'd hope my proteins are all held together by very unreactive bonds that won't react and break and all that stuff. So it's a good thing they're linked by peptide bonds. So the peptide bond is an amide bond. That's the first part. So, and one thing to note, this amide bond actually has a fair amount of delocalization. We can look at it as resonance here. And so if I look at this, the resonance structure I could draw, and I'll just kind of draw part of it here. Thought you could forget all about resonance and stuff, didn't you? So this delocalization, this resonance, if you will, is actually pretty appreciable. And that's important for a couple of different reasons. Cool, you thought you could forget resonance after OChem, didn't you? So if you look, in this case, that bond right there is a single bond. In this structure, it's a double bond. What is it really in reality? Which I guess what does it really means? Somewhere in between. It's between a single and a double bond. But the key is that because of this resonance, if I didn't realize there was resonance, I would just think, oh, it's a single bond. So, and single bonds can freely rotate, as long as they're not part of a ring anyways. They're just allowed to freely rotate. And it gives a lot of flexibility into a structure and stuff like that. But double bonds, on the other hand, what's a pi bond? The second bond in two bonds, the second one's a pi bond. And what is a pi bond? It's side-to-side overlap of p orbitals. They're side-to-side. If you rotate that bond, you wouldn't have side-to-side overlap anymore. And you can't rotate around a double bond. And so in this case, because this has a significant amount of double bond character, I think somewhere around like 40% double bond character, because of that, this bond here, regardless of how you draw it, it's not free to rotate to any appreciable degree. It's very planar. If you looked at, from OChem back in the day, a carbon-carbon double bond, a typical carbon-carbon double bond, what hybridization would these carbons in all likelihood be? sp2, and the geometry around an sp2 hybridized atom is trigonal planar. And so what you find out is that these two atoms are in the same plane, and the 4 additional atoms they're all attached to are all in the same plane. This is a big, fat trigonal planar being the key word here, structure. And so the same thing happens in your peptide chain. So around this bond, the nitrogen and the carbon, who are double bonded together, and the 4 atoms they're attached to are all in a rigid planar structure. Now, notice I'm not doing the line angle, but you might be expected to figure out how all 6 of these, it's these 6 in particular, are in a plane. And again, the key is find out where that partial double bond character is, and it's also the 4 atoms they're bonded to. That's where we get some planarity in the structure. Cool. And this just has some consequences on, protein folding and conformations of proteins and things of this sort. But suffice to say, you might just need to be able to identify those 6 atoms that are planar due to this kind of resonance that's going on.